Okay, so we have been talking about planning domains, and we have seen that planning domains can be described by planning domain description languages, or PDDL as we are called, and we have looked at the simplest of those languages called PDDL 1.0. What a planning domain description language gives you is a set of predicates which you can use to describe the state, and a set of operators which have certain predicates as preconditions and certain predicates as post conditions, which means that if that action or the operator is applied, first of all it can be applied only if it is applicable, and if it is applied, then its post conditions are brought into effect, which means from the state description we delete some predicates and we add some predicates. In fact, the original strips planner had something called a delete list and an add list, but nowadays we say effects positive and effect negative. So, they are basically the same thing, just different ways of saying it. So, given a planning domain, let us see how forward state space planning works, and this kind of corresponds to the kind of search that we started with. We said that you start with the start state and head towards a goal state. So, when is an action applicable? Given a state S, an action A is applicable in the state S if its preconditions are satisfied in that state. Essentially, remember that every action has a set of preconditions which we had denoted by a list, which can be the list of preconditions or a set of preconditions. And remember that the state itself is a set of statements, that on A B is true, on B C is true, and things like that. So, it is a set, and preconditions are also a set. So, for example, arm must be empty, A must be clear. So, that set must be a subset of the state that we are talking about. If that is the case, then we say that the action is applicable essentially. So, as we had mentioned earlier, unstack AB is applicable because arm empty was empty in the given state, on AB was true in the given state, and clear A was true in the state. And then of course, we saw the effects. The positive effects were that we added holding A and clear B, and the negative effects were that we deleted arm empty and on AB. So, we are in the process of formalizing that here. We say that a state progresses over an action if when an applicable action A. So, first of all, this action must be applicable, is applied in a state S, then the state transitions or progresses to a new state S prime, which is basically denoted by the fact that a state transition has happened, as we said earlier, but it is computed in practice as follows, that from the state S to the state S you add the positive effects of A. So, this is union. So, you take a union of these two sets, and this is set difference. You subtract in some sense the negative effects of A. So, we saw that in the previous example that we just discussed. If you were to apply unstack A from B, then you add these two things, holding A and clear B, and you delete those two things, which is arm empty and on AB essentially. So, the negative effects are subtracted and the positive effects are added to that. So, a plan, and we will use pi to stand for a plan in general, is a sequence of actions A1, A2 up to AN essentially. It is a linear sequence of actions. Later on we will see whether we can have actions, plans in which actions can happen in parallel, but for the moment we will assume that they just is a sequence of actions. So, it is a sequence. A plan pi is applicable, the whole plan is, it is like a compound action, you can think of it. Instead of saying just one action A, you are doing a sequence of actions. So, you can think of it as a macro operator or something like that, but in general the terminology we use is that a plan pi is applicable in a state S0 if there are states S1 up to Sn such that for each Si which is more than S0 is computed by progressing from Si minus 1 using the action Ai essentially for all I is equal to 1. So, you start with S0, then apply action 1 and you go to S1, then you apply action 2 and go to S2 and so on. You do this for n actions and eventually you will reach a state of Sn, which we write as saying that we have progressed over the plan. So, the argument here is pi here, which is the plan, as opposed to a single step progression where the argument was an action. Here it is a full plan. So, the final state is reached after all the action, after we have progressed all the actions A1, A2 up to An. We say that this plan pi is a valid plan. So, let G be a goal description. It is again a set of predicates that are true. Then plan pi is a valid plan in a state S0, which is where we start applying the plan, if the goal description is a subset of this state that has been reached by progressing over all the actions of the plan. If in that state, so remember Sn is the state. So, essentially what we are saying, G is a subset of Sn if there are n actions in the plan, which is equivalent to saying that G is a subset of gamma S0 pi, because we have said above that Sn is equal to that essentially. The final state is the state that results after all those actions in the plan have been applied essentially. And if the goal state happens to be a subset of that, or the goal description happens to be a subset of that, then we say that the plan is a valid plan. Now, the simplest thing, as I said, was forward state space planning. And so, you are in a given state which is described as shown in the picture there. And so, let us say that is a given state or the start state, and then you can do various things. You can see that you can unstack A from B as shown here, or you can unstack C from D, or you can unstack F from G, or you can pick up J as shown here, and so on also. So, you can see that this is like the move gen function. The move gen function says that from the given state, these are the actions that you can this thing, but of course, we have not described the resulting state. We know that we can do that by progressing over each of those actions. But the important thing to see here is that all the actions that are applicable will be considered by forward state space search essentially, which means the larger is the domain description, the more will be the number of actions and the more will be the branching factor. We will see that that is in some sense a little bit of a drawback about forward state space planning. So, for example, if you were to pick this action unstack A from B, which is an applicable action, then from that state you will be holding A essentially. Supposing with that, then what would be the state look like? That the robot arm will be holding A and A will no longer be on the B. So, it would have been deleted from this state essentially here. And then what are the actions that are applicable there? You can, first of all, you can put A back onto B, or you can put it on top of C, or you can put it on top of F or J or K or P, or you can even put it on the table. All these actions are possible. So, there is a huge state space that is happening. So, I have shown this that after unstack F from G, you can either put down F, or you can put it on A, or you can put it on C, or on G, or on J, or on K, or on P essentially. That is how the search space is generated essentially. How do you navigate this search space? That is one of the algorithms that we have spoken about, can be used, breadth first search, depth first search, and if you can think of a heuristic function, then we could use one of them. We saw that when we were looking at hill climbing. So, what is the drawback of forward state space search? That the tree is huge in the sense that it is a very high branching factor. Now, we have said that The given state is completely described, which is why all these different actions are possible, are applicable. But the goal description is not completely described. The goal description only says what do you want to be true. So, for example, if I only wanted that this to be true, that L should be on G, for example, and nothing else. I do not care about what else is happening, that in my goal state L must be on top of G essentially. Then you can see that if you reason backward from the goal, then there are not too many options that you can see to make the goal true essentially. So, there has been a opinion not only in planning, but in other forms of reasoning, is that goal directed reasoning is more tractable than forward reasoning or state space reasoning. So, if you were to study logic, you would see that that forward chaining, which is a term that we use in first order logic, has high branching factor, and backward chaining has low branching factor. And the reason for that is that the backward chaining or backward planning, as we will call it, backward state space planning, is more focused on achieving the goal. What is the goal? The goal says that on LG must be true. Let me write it here. And this is all that is there in the goal state. Then you simply want to see which actions will make this true and think about those actions while constructing the plan. That is what backward state space planning does, and we will look at that now. So, forward state space planning has a high branching factor. This is because the state is completely described and many actions are applicable in any given state. Without the guidance of a good heuristic function, search may become computationally very expensive. On the other hand, the goal description is often quite small. So, in the earlier example that we saw, where we described the planning problem, the goal description was only two things, that you wanted G to be on A and you wanted B to be on G, and therefore, search can only focus on that essentially, and that is what backward state space planning will do. Backward state space planning works from the goal description and moves in a backward direction towards the start state essentially, and you can imagine that the branching factor would be lower essentially. So, will it be more efficient? Because only actions that are relevant to the goal will be considered essentially. Of course, we have to define what do we mean by relevant actions, and we will do that. Let us explore this possibility of backward state space planning. So, in backward state space planning, first of all we have to talk about a relevant action. What is a relevant action which will achieve something in the goal that you are interested in? So, we are given G. Remember that these are sets of predicates. This is true, on AB must be true and on BC must be true, or something like that. Sets are there. And action A is relevant. Just as we talked about applicable actions in forward state space planning, we talk about relevant actions in backward state space planning, and it is relevant to a goal. If it produces some positive effect in that goal and it deletes nothing from the goal essentially. If that condition is true, then we say that the action is relevant, and you can see that there are two conditions, that the positive effects of that action A intersected with G, that is the goal description, must not be an empty set. There must be at least one positive effect that it is adding to the goal state, and also that the negative effects of this action intersection with G must be an empty set, which means it is not deleting anything from the goal state. It is only adding something to the goal state, and because the goal state is something that we want to make to be true. We will see examples as we go. Just as we could do progression in forward state space planning, we can do regression in backward state space planning. So, if a relevant action A is applied in a goal G, then the goal regresses to a new goal which we call G prime. Sometimes we call this a sub goal, but we often use a terminology goal for such things, defined as, you can see that there is an inverse here, gamma inverse of the transition function. You are going from G to G prime, you are going in a backward direction, and how do we compute that? if there are anything which is a positive effect of this action, then we delete, if that is present in the goal, then we delete it from the goal. Remember that this slash stands for set difference, that it is like saying G minus this set, and what is that set? That set is the positive effects of this action A, and why are we deleting it? Because it is a positive effect of the action A, and if you are going to do this as a last action, then maybe that is a way of achieving those positive effects. So, we do not need to be there in the sub goal essentially. So, we delete that from there, but for that action to be applicable in the previous state, its preconditions must be true in the previous state. So, in the sub goal, remember that this is the sub goal G prime that we are trying to compute, we must add the preconditions of A. So, we delete whatever that action A is going to achieve anyway for us, but for that action A to be applicable, its preconditions must be true. So, we add that to the sub goal G essentially, and this is a step we will see an example shortly. This is a step we call that you are regressing from a goal G to a new goal or a sub goal G prime essentially. So, what must G prime, what must be true in G prime if that last action were to happen essentially? We will see that that is the last action, because that is just before the goal is achieved. So, again we talk about a plan pi is again it is a sequence of actions as before. We say that a plan pi is relevant to a goal G of n if there are sub goals going right up to G0 from G of n minus 1 up G0, such that for each Gi and the relevant action Ai, you regress to a sub goal G of I minus 1, and you do this for all the n actions. Remember, there are n actions. This is An is the last action, then we have the second last action, then the third last action, and so on and so forth, right up to A1, and A1 will regress to S0 or G0. So, this is a goal description that is a result of regressing over the entire plan starting from G of n. So, this step that we have of going back one step, which is described here, we do from the last action to the first action A1 and end up in something called G0. A plan is a valid plan if this G0 that we arrived at here is true in the state S0. And what do we mean by true in terms of computation? It means it is a subset of the set of predicates which describe S0. S0 is the start state essentially. So, essentially we are saying that a plan is a valid plan if Gn is a subset of, okay, there is an error here, it should be minus 1. We are regressing over the states, this thing. But as we will see shortly, there are pitfalls here, there is not a free lunch. But the validity of a plan, and we will see this, is still checked by progression. What do we mean by that? That you are given a plan pi which is A1, A2 up to An. Is this a valid plan? We already know how to check for whether it is a valid plan, is that you progress over action, progress not regress. You start at the start state S0, progress over A1, then progress over A2, then progress up to An, and then see if the resulting state satisfies the goal condition.
So, my question is, in the forward state space planning, we are taking the initial S0 and moving to the final state Sn.
I mean, we are generating a tree
but
and somewhere there are some goal nodes.
Multiple branching factor. But in backward state space planning, we are taking the reverse approach. But my doubt is, even if you take the reverse approach, it will construct a tree with a multiple branches similar to the forward state space planning.
Yeah, right? But the branching factor will be low. As
I don't understand how it would be low.
Because in the start space that we had some 10-15 actions possible. There were many columns of blocks, each of them could be done. In the goal description, there were only two things that we, in the small example we saw, there were two something, let's say some A must be on B and B must be on C. So there are only two actions which will achieve that, and all the other actions are not relevant. So there are only two relevant actions, whereas in the forward state space planning, because the state description is complete, there are many applicable actions. So that many versus few is what gives an advantage over backward state space planning, but we will see in a moment that there can be problems that we have to address. So let us look at this example, that okay, this is a goal description given to us, that G must be on A and B must be on J. The start state may be the huge state that we had seen some time ago essentially. So backward state space planning does not care about that. It says, okay, you have given me this goal description and let me see how to achieve that goal. So there are two predicates in the goal description, that on GA must be true and on BJ must be true. Now we want to look for relevant actions for achieving each of these two predicates. How can on GA be made true? On GA can be made true if the last action is stack G onto A. If the last action was stack G onto A, then on GA would be made true. Likewise, on BJ would be made true if the last action was stack B onto J. So there are two relevant actions only in this small domain, and that is what backward state space planning does essentially. So if you look at the stack operator, why is stack xy a relevant operator or stack G from A? Because it has a post condition on xy, which is something that you want to achieve. So there are two predicates of the kind on xy, on GA and on BJ essentially. Because it produces that, remember that an action is relevant if it has a positive effect which is there in the goal. This stack GA is relevant because it has a positive effect which is on GA. As you can see, it is a positive effect of the stack action, and also it must not delete anything from the goal. That was the other condition that we had for an action being relevant. The only thing it is deleting is clear Y essentially. What is clear Y? It would correspond to delete clear A essentially, but that does not affect our goal. We do not care if there is something, whether we have not stated whether A should be clear or not clear. So that does not matter. In a sense, we have not explicitly stated that A should not be clear. It will be not clear, or it will be not clear as a consequence of this stack action, because once you are stacking x onto y, y will no longer be clear, but that does not affect our goal description. Our goal description is very limited. It is only focused on whether on GA is true and on BJ is true essentially. And so one of the two relevant actions is stack G onto A. If that was the last action, then something in the goal would be achieved, and that something is on GA. Now, how do we regress from the previous state? So, first of all, we have to add the preconditions of this stack action. What are the preconditions of the stack action? That you must be holding G and A must be clear essentially. So, this part is added, which is what we said, that you take the union of something and the preconditions of A. So, this part are the preconditions of this action stack G comma A, and we have added it to the. So this G is a little bit confusing, because here G is the name of a block. So let me use the term goal here. If this is the goal, then this is the goal that you regress to, which we call as a goal prime, let us say. So, when you go from goal to goal prime, you have to add the preconditions of the action that you are regressing over, and the preconditions of stack G A are holding G and clear A, and that is why in goal prime you can see that we have added these two. So, we have added these two things here. If there are any positive effects of this action, we should delete it from goal prime. So, if on G A was already true from that in the goal description, we would have to delete it. That is according to the rule, but it is not true, and neither is arm empty true. So, it does not matter. So, the only effect in practical terms we have is that we started with this goal which had two predicates, on G A and on B J. Okay, sorry, yeah, we did delete this. We did delete this predicate, which is the positive effect of this thing. So, we delete it from there, and then we add the preconditions. So, this is deleted and this is added. And of course, that on B J was there in the goal and it continues to be there in the goal prime, that is not being affected. So, the only effect of saying that the last action is stack G of A is that you must have begun from a state in which this goal was true, which means that in that state, which is goal prime we have called it, holding G must be true, clear A must be true, and on B J must be true. And if in that state you had applied action stack G of A, then you would achieve the goal state that you want to achieve. Okay, so that is one this thing. What would be the next stage? The other action is that you could have stacked B onto J, and it has a similar condition, as you can see that the preconditions for stack B on J are holding B and clear J, and you have added that to the goal prime, and you have deleted on B G A, but you have left this on G A to be true. So, the other goal carries forward to the this thing, and you have deleted this one on B J, but you have added the preconditions. So, that is the regression operator. Now, if you are doing backward state space search, then you will say, okay, how do I achieve this new goal which I have called as goal prime? You could do various actions. You could say pick up G. Why is pick up G relevant? Because its effect is holding, that this is an effect of positive of pick up G is that you will be holding G, and holding G is in your goal essentially right, or in your sub goal essentially. Or you could say I can be holding G can be made true if you unstack G from somewhere else essentially. But of course, then the question would be what is X? What are you unstacking it from? If you look at the predicate clear A, which is true in goal prime, or which needs to be true in goal prime, it could be made true by an unstacking something from A essentially. If you unstack something from A, then A will become clear. So, if clear A to make clear A true, one way to do is to unstack X from A, but unstack would be needed only if clear A was not true essentially, but backward state space planning is not aware of that essentially. And of course, the predicates which is still around, that on B J must be true. So, we could say stack B J is an option. So, what are we saying here? We are saying that this is the last action in your plan. If that is the last action, then you go to this sub goal, goal prime, Now, to achieve goal prime, this is the second last. You are simply going by the definition of applicable relevance and regression essentially. But the problem with this choosing this stack Pj as a second last operation is that how can you stack B onto J and end up holding G in the resultant state. So, here is a tiny example. The given state is on the left hand side, there are 3 blocks ABC all are on the table, and the goal state is a simple state that B must be on C and A must be on B essentially. So, which is of course described on the top right, you can see as a goal description. So, starting with that goal G, you can use stack A on B as we just saw an example, that stack A on B is a relevant action because it achieves on AB. So, from there we have deleted this and we have added this and we have added this and we have got this new goal which is a sub goal. On BC continues to be there in the goal, that we still want that to be true, but we now want holding A to be true and clear B to be true. If that is the case, in such a state you could have applied stack AB and achieved the goal that you wanted, which is on AB and on BC. On BC is already true in this sub goal G prime, as you can see. Now, we look at this G prime. So, this was G and then from G we regress to G prime, and now we are asking how to make G prime true. Stack BC is relevant because it achieves on BC. So, it is a relevant action. So, we are saying okay, the last action is stack AB, the second last action is stack BC, but you can already see that in the regressed goal, which is G prime prime, there are 2 predicates which cannot be true at the same time, holding A and holding B. How can they be true? We are working with a one armed robot and we have already said that it can only hold one block at a time. But here in this goal, we are saying we want to be in a state in which it is holding A and it is holding B, but the backward state space planning as we have defined, how have we defined it? We have defined relevant actions and we have defined the regress function and we have defined the goal test condition essentially. It is not aware of this discrepancy which is happening. In fact, there was a group of researchers which in the mid 90s, they tried to write a program which will look at a goal description and try to find out whether it is consistent or not. So, there was a program called TIM. I do not remember the authors right now. Which tried to check for consistency of this essentially. But in the absence of that, we just progress with our planner, or in other words we regress to new goals. So, now we have 4 sub goals here, or 4 goals in this sub goal G prime, or 4 predicates in this sub goal G prime, and we choose a relevant action. What is a relevant action? Pick up A. Why is pick up A relevant? Because it gives us this thing which is holding A essentially. So, when we regress to G triple prime, we will delete holding A from the description, but we will add instead the fact that A must be on the table and A must be clear, and I forgot to add, we should also add arm empty to that. So, that will get added to that. So, again you can see that there is going to be an inconsistency. If your arm is going to be empty and if you are going to be holding B, then that is not possible. But backward state space planning cannot see that. Then it has all these sub goals, all these predicates in the sub goal, and it picks a relevant action which is pick up B essentially. Why is pick up B relevant? Because it gives you this predicate holding B essentially. And then you can see that now we have reached a sub goal which says on table A, clear B, on table B and clear C. Now, this sub goal which we called as G0 at some, when we were talking about regression, you can see that on table A is true in the given start state. So, this is true in what we call as the start state or S0. On table is true because you can see on the figure on the left that all these predicates are true. On table A is true, there is nothing on top of A, so clear A is true. There is nothing on top of B, so clear B is true. On table B is true in that figure, and clear C is also true essentially. So, everything is true. So, our algorithm can terminate essentially by saying that when this sub goal, which we have called as let us call it G 4 times. I had used subscripts, but anyway I have started using this G prime, and or let me write it like this, that we have reached this sub goal, this thing, and this is a subset of start 0 essentially, which is a given start state to us. All these predicates are true in the start state, so we can terminate.
So, if I am not mistaken, it should include the on table C as well, right?
The goal does not talk about where is C. The goal only says that, see, while I have drawn it, I have drawn it on the table, but when I have given the goal description, I have not given that. I have only said that on AB and on BC is all we care about. So, it is not there in the sub goal, it is not there in the sub goal, it is there in the start state.
Yeah, that's what I'm saying. In S0, the last thing, when we reach the S0, it should be include the on table as well.
Yeah, S0 includes on table C, but G 4 primes is what is described here essentially, and that happens to be a subset of S0. So, that is a termination criteria. So, this illustrates how backward state space planning may find a plan. What is the plan? Pick up B, pick up A, stack B onto C and stack A onto B. But we have seen already that on the way there were these spurious states, holding A was true, holding B was true in some goal state, or arm empty was true and holding B was true in some goal state, and that we observed that it is not possible, but we said that backward state space planning cannot see that. So, it goes ahead and says I have finished finding a plan, and why has he finished finding the plan? Because this condition is true, that the sub goal is a subset of the start state. So, I have reached the start state. So, now what do we do? For our planner to be correct, we do a check. Remember that we have a check for a valid plan. What is the check? So, what is the plan to start with? Search terminates because the regress goal is true in the given state essentially, which is those 5 predicates. But when you look at this plan, pick up B, pick up A, stack B on C, stack A on B, it is not a valid plan. How do we do that? We know that how to check whether a plan is a valid plan. We do that by progressing with this plan. So, this is pi, and when we progress over this plan, we have said that we represent this as using the gamma function repeatedly over pi, and we reach a state essentially which is the goal state. And if the goal is a subset of this, then we can say that the plan is a valid plan essentially. So, we need to progress over this plan. What is the plan? On table A, sorry, what is the plan? Pick up B. The last action, the first action is pick up B. That is possible. You can, what will happen when you do first action? When we progress from here after pick up B, what is the world going to look like? That this B is going to be held by this robot, and A will be on the table and C will be on the table. That is a new state. After you have progressed over the first action, which is pick up B, then you want to progress with the second action, which is pick up A. pickup A is not applicable at all. Why? What are the preconditions for pickup A? That A must be on the table, which is true, but arm must be empty, which is not true. So, this is not a valid plan, because you can't do this sequence of actions and end up in a state which is which satisfies the goal state essentially. So, that is a problem with backward state space planning, is that you may end up with spurious actions and spurious states, and we have to do this extra check essentially. As I said, there was this program which some people wrote to try and check whether every state that you are regressing over is consistent or not, but it is not a simple problem, otherwise people would have incorporated that.
So can I sort this progress, the plan in such a way to make it valid plan? Will it be possible?
No, no. So, you are talking about a new approach to planning, that start with backward state space planning, come up with a plan, and then sort this thing. In this example, it appears that that may be the case, because essentially what you want to do is to pick up B and then stack B onto C, which is there in that action, and then pick up A, this thing. In this, because these are the only 4 actions in the final plan, it may be possible, but for more complex problems, and we will see some more complex problems, it may not be possible. I do not think so. When you are talking about looking at a permutation of these actions, right, that you have these 4 actions and try different permutations, and one of them will work, but then finding permutations is going to be a large space. Remember that when we talked about the TSP problem, we said that taking there are n factorial permutations of n objects essentially. So, it might be feasible, but does not sound like efficient, something which is efficient.